In the last lecture, we had examined binary diffusion in situations where the flux of material due to concentration gradients can generate a transport of the center of mass or a center of mass velocity. And we had examined how the diffusion, the Fick's law for diffusion is formulated in such cases. You have to take into account the fact that when the diffusion takes place of one of the components, there is also a center of mass velocity, okay? And that has to be incorporated, whether it is done in the mass average formulation or the mole average formulation. As I had said, the mass average formulation is the correct one when we are dealing with fluid flows, because the fluid momentum is defined based upon the mass average velocity of the mixture. Okay. So, in the momentum equation, it is the mass averaged concentration velocity that enters. Okay. However, there may be situations where it is more advantageous to take it to formulate it in the mole average sense, especially in gases, for example, where the molar concentration is a constant at a constant temperature and pressure. The mass average concentration is not necessarily a constant at constant temperature and pressure, and in those cases a mole average formulation is more appropriate. Okay. And I had solved for you two such problems. The first was the drying of water, the evaporation of water through a tube into dry air, and in that case I told you that the molar flux of air is much smaller than the molar flux of water, and therefore we can neglect the molar flux of air and consider the molar flux of water alone. And if you do that, the equation for the flux is actually a nonlinear equation in the mole fraction of water. Okay. And you have to take that into account in order to calculate the time required for evaporation. I should note here that the Fick's law for diffusion is expressed here in terms of the mass fraction or the mole fraction rather than the concentration itself when you are considering binary diffusion or multi-component diffusion. Similarly, in the case of the formation of iron pentacarbonyl, in this case we have a stoichiometric ratio between the reactants and the products, and because of that the fluxes of carbon monoxide and iron pentacarbonyl are related. Okay. The fact that carbon monoxide is coming downwards and iron pentacarbonyl goes upwards implies that the ratio is actually negative, and the magnitude is determined by stoichiometry in this case. Okay. So, so those are the complications that arise when you have to deal with binary diffusion, where the diffusion process itself generates a center of mass. In this lecture, we will start looking at correlations in balance equations. Okay. So, for example, the simplest example I can think of is, for example, a sphere that is cooling in air, okay, or in a fluid with the temperature T infinity far away and temperature at the surface as, let us say, T naught. Okay. At the surface you fix a temperature and the temperature far away is T infinity, and one would like to know what is the flux, the average flux of heat in this case, and how is that related to the temperature difference and the diameter d of the sphere, okay, and other parameters. Okay. So, how is that related to the thermal properties, the fluid properties? We had derived correlations in this case. For example, you will recall that for heat conduction from a sphere, the correlation was that Nusselt number is equal to 2. Okay. It has to be a constant in the limit of low Peclet number if there is no flow around the sphere, okay, and that constant is equal to 2, which is the ratio of the average flux by a quantity which has the same dimension or the same form as the right side of Fick's law of diffusion. Okay. Similarly, if there was a flow past this, okay, so if there was a flow past this, okay, this object in the limit of low Reynolds number and high Peclet number, we had derived a correlation, okay, or we had not derived it, I just given you that correlation, and I said we will see how to derive it later in the course. Okay. It's equal to 0.992 times the Peclet number power 1/3, okay, where the Peclet number is equal to if this velocity is, if the free stream velocity is Vfs, this is equal to Vfs d by alpha, the thermal diffusivity. Re is equal to rho V free stream d by mu, and yeah, the Nusselt number I had already given you. Okay, so okay. Now, what if instead of having a constant temperature on the surface, the sphere is actually cooling with time? Okay, the sphere temperature is actually decreasing with time because it is cooled by the surrounding air, either in the conduction dominated regime. So, I should note that this is for PE much smaller than 1. Okay. When the Peclet number is much smaller than 1, it means that convection is small compared to diffusion, and therefore, convection can be neglected altogether and the Nusselt number has to be 2. Okay. What if the sphere is cooling? Okay. In that case, what happens? Can we still use this Nusselt number correlation in order to determine the rate at which the particle is cooling in time? Okay. When the correlations are derived, it is assumed that the system is at steady state, okay, that is the temperature is a constant. Okay. At steady state, you know, in the case of diffusion dominated flow, okay, in the case of diffusion dominated flow, okay, the diffusion of heat from the surface takes place over a distance comparable to the particle diameter d. The characteristic diameter is d, and therefore, the characteristic length for diffusion is d itself. Okay. In this case, for P less than 1, what is the diffusion time? Okay, that is, if I instantaneously place the sphere at this location, okay, the sphere, let us say, was at initial temperature T infinity and the fluid temperature was uniform T infinity everywhere. Okay. Temperature was a constant, okay, everywhere on the sphere, within the sphere and in the fluid, and instantaneously I increase the temperature at the sphere surface itself to T naught. How long would it take for the temperature profile to evolve to its final steady state if the temperature is instantaneously increased to T naught? Okay. That is the diffusion time, the time it requires for the heat to diffuse from the sphere and reach a steady state temperature profile around the sphere. Okay. That is the diffusion time in this case, and that diffusion time, okay, just from dimensional analysis you can see that that diffusion time is equal to d square by alpha, where alpha is the thermal diffusivity. Okay. That diffusion time is equal to d square by alpha, where alpha is the thermal diffusivity. That is the time it would take for the temperature profile to develop to its final steady state profile after the sphere temperature has been instantaneously increased to a higher value. Okay. And as the sphere temperature changes, that is the time it would take for the temperature to adjust to the sphere temperature, the profile to reach a steady state value, which is the same as you would have had if the sphere were at steady state. Okay. That is the time, development time for, or the diffusion time for the temperature profile. And the Nusselt number correlation is valid only when the temperature profile has reached its steady state value. Okay. We will calculate that later, but the Nusselt number correlation is valid only when the temperature has reached its steady state value. Okay. Therefore, the Nusselt number correlation can be used only when the temperature, the time required, the time scale for the variation in temperature of the surface. Okay. The time scale for the variation in temperature of the surface is much larger than the time required for the steady state temperature field to develop. Okay. In that case, you can assume that the temperature field has developed instantaneously in comparison to the time taken for the variation in temperature, and then you can use the correlation. Okay. So, the correlation is valid only when the characteristic time for the variation of the temperature of the sphere of the boundary, okay, is much longer than the time taken for diffusion or the time taken for the system to reach steady state for that particular value of the temperature of the surface of the sphere. Alternatively, the assumption being made here is that the steady state temperature profile, temperature field has formed at each instant, and the flux is the value that would have been given if the field was at steady state. Okay. So, under those conditions you can use the correlations, the Nusselt number correlation for example, in order to determine what is the temperature variation with time of the sphere. Okay. In addition, if you were to have, let us say, a long or slender object, a cylinder say, okay, if you had a cylinder, okay, if you had some slender object like a cylinder, okay, in which the temperature was varying as a function of position. Okay, let us say this was a fin on a heat exchanger and the temperature was varying with downstream distance, okay, in this heat exchanger. So, let us say that we had a long and slender object here with temperature T naught on one side and T infinity on the other side. The temperature, and it is immersed in a fluid, then there is going to be heat transfer from the surface of the object due to conduction or due to convection, natural or forced convection, and the temperature will vary along the length of the object. And in that case, the question is, can I use a correlation locally for each differential surface area of this object based upon the local temperature here, the difference between the local temperature here and the temperature T infinity far from the object, in order to find out what is the heat flux or the rate of heat transfer from that differential length of the object. Okay. That you can do provided the length scale for the variation of the temperature along the object is much larger than the diffusion length, the length scale over which the energy or the mass diffuses away from the object. Okay. Provided that the length scale for the diffusion along the change in temperature along the object is much longer than the length scale for diffusion from the object. Okay. In the case of low Peclet number transport, where transport is dominated by diffusion, the characteristic length for diffusion is always equal to the characteristic length of the object. In the case of a cylinder or a slender object, for example, the characteristic length is comparable to the longest dimension of the object, and therefore, one can never assume that the length scale for diffusion is much smaller than the characteristic length of the object. And therefore, you cannot use a description where you use a correlation for the local heat or mass transfer at a given location from the object. Okay. However, at high Peclet number, we will see that there are situations in which the characteristic length for the variation of temperature is much longer than the length scale for diffusion from the object. Okay. We will see that a little later. So, as far as diffusion dominated flows are concerned, transport, you can use correlations provided the characteristic time Tc, the characteristic time Tc for the variation in temperature of the surface of the object, for the variation temperature of the surface of the object is much larger than the diffusion time. Okay, the time required for the steady state temperature profile to develop, temperature field to develop around the object when there is a change in the temperature at the surface of the object. Okay. So, let us consider an example here. Okay. So, we have we will take this particular configuration and consider natural convection. There is no velocity. Temperature at the surface is equal to I will call it as T. Okay. Temperature at the surface is equal to T. Okay. And the temperature far from the surface is equal to T infinity. Okay. So, the sphere diameter is d. Okay. The density is rho s for the sphere, the specific heat is Cps. Okay. And for the fluid, density, this I will call it as rho f. Okay. Specific heat Cpf, conductivity Kf, and I will assume that the conductivity of the sphere is sufficiently large that the temperature is uniform throughout the sphere, and that is equal to the surface temperature. Okay. The temperature is uniform throughout the sphere, and that temperature is equal to the surface temperature of the sphere. Okay. Like if you have, for example, a metal, okay, cooling in air, for example, then the conductivity of the metal is much larger than the conductivity of air, and therefore, I can assume that the surface temperature is the same as the temperature within the sphere. That is, the temperature has equalized over the entire sphere over a time scale small compared to the time scale for the evolution of temperature in the fluid, because the conductivity of the sphere is sufficiently large. Okay. So, how do I find out what is the rate of change of temperature of the sphere with respect to time? Okay. From a energy balance equation, okay, the mass of the sphere times the Cp of the sphere times the rate of change of temperature. Okay. This is going to be equal to the rate of change of the energy, the thermal energy of the sphere, mCp times the rate of change of temperature with respect to time, is equal to the rate at which energy is lost. Okay. The rate at which energy is lost is equal to the average flux times the surface area. Okay. Okay. With the negative sign, because as the heat energy is lost from the surface of the sphere, T is greater than T infinity, energy is lost and the temperature of the sphere decreases with time. Okay. So, that is the balance equation. Okay. Now, I can write this in terms of the density and the diameter of the sphere, because the mass of the sphere is equal to pi d cubed by 6 into the density of the sphere. Okay. Okay. So, I have pi d cubed by 6 rho s Cps dt by dt is equal to minus. Okay. For QAV, I will use the Nusselt number correlation. Okay. For QAV, I will use this Nusselt number correlation for heat conduction from a sphere. Okay. So, I have minus of 2 2 k delta T by d into pi d square. Okay. And I cancel out the pi on both sides, and I can cancel out the powers of diameter, and I will get finally that dt by dt is equal to minus 12 k d square by rho s Cps, okay, into delta T, which is T minus T infinity. okay, into delta t, which is t minus t infinity. Okay. So, that is the equation for the temperature field. Okay. And you can see that this can be written as minus of t minus t infinity divided by the characteristic time c, T c, okay, the characteristic time, okay, where this characteristic time, okay, T c is equal to rho s C p s by 12 k d square. Okay. Okay, that is the characteristic time. Sorry, there is a d square should be, I made a mistake here. Yeah, this, the d square should be in the denominator, okay, because I have a d cubed here and I have d on top here and 1 over d. So, the right side is proportional to d, the left side is proportional to d cubed. So, when I divide through it, I get a 1 over d square. Okay. Therefore, the characteristic time is rho s C p s d square. Okay. So, that is the characteristic time, and I can simplify it further by expressing it in terms of the thermal diffusivity. Okay. This is K f here, which is the thermal conductivity of the fluid. Okay. I should use a K f everywhere. Kindly change K to K f everywhere, because I am using the thermal conductivity of the fluid. Okay. I know that the thermal diffusivity is equal to K f by rho f C p f. Okay. So, I can substitute alpha as alpha f, K f as alpha f, rho f and C p f. So, this will give me rho s C p s d square by 12 alpha f rho f C p f. Okay. And you can verify that this has dimensions of time, because the density and the specific heat will cancel out in the numerator and denominator dimensionally, and what you end up with is d square divided by alpha f. Okay. D is a diameter and alpha is a thermal diffusivity. So, it has dimensions of time. Okay. Once I have this, then I have an equation for the temperature field. Okay. I can integrate this equation, okay. I can integrate this equation, okay, dt by dt is equal to minus of t minus t infinity by T c, okay, and you integrate it once, you will get log t minus t infinity is equal to minus t by T c, okay, plus a constant, and t minus t infinity is equal to e power some constant, that is e power c e power minus t by T c, and this constant is determined from the condition that at t is equal to 0, the temperature is the initial temperature T naught, say. Okay. The temperature is the initial temperature T naught, okay. And therefore, the solution for the temperature becomes T minus T infinity by T naught minus T infinity is equal to e power minus T by T c. Okay. So, therefore, the temperature field decreases exponentially with time. Okay. In this case, if we assume the steady state approximation for the temperature field around the sphere, and therefore, the heat flux around the sphere. Okay. If we assume the steady state approximation for the temperature field around the sphere, and therefore, the heat flux around the sphere. And finally, we have to examine the assumption that the T c, okay, T c, okay, under what conditions is the characteristic time, the time scale for the evolution of the temperature of the sphere surface, under what conditions is that large compared to the diffusion time, okay, the time scale for diffusion. Okay. So, if I take the ratio T c by T d, okay, which is equal to rho s C p s d square by 12 alpha f rho f Cpf. Okay. That is the time scale for the characteristic time for the evolution. Okay. The time for diffusion is d square by alpha f, as I already told you. Is the characteristic length scale divided by the diffusivity is the time scale for the development of the temperature field around the sphere if you have instantaneously increased the temperature of the sphere to some value that is different from the surroundings. Okay. And you can see that this ratio, okay, the d square and the alpha will cancel out, and the condition is that, okay, Tc by Td is equal to rho s Cps by 12 rho f Cpf. Okay. So, therefore, the steady state approximation can be used only when the density times the specific heat of the particle is much larger than the density of the times the specific heat of the fluid. Okay. When the density times specific heat of the particle is much larger than the density times specific heat of the fluid, then the time scale for the characteristic time for the decay of the temperature difference, okay, the characteristic time for the decay of the temperature difference is much larger than the diffusion time, and at each instant you can consider the diffusion to be a steady state process, and the Nusselt number correlation is valid for a steady state process, and therefore, you can use the Nusselt number correlation for diffusion here and calculate what is the diffusion, what is the evolution of temperature with respect to time. Okay. There are situations where not just the temperature of the surface or the concentration at the surface changes, but where the dimension of the particle also changes. Okay. There could be situations where the particle, for example, in the case of evaporation, there could be the particle diameter decreasing due to evaporation, and similarly in the case of sublimation, you could have a solid particle whose diameter decreases with time. Okay. And in those situations as well, there is an evolution in the temperature field, not because of the surface temperature is changing, but because the diameter itself is changing. Okay. So, as the diameter changes, the temperature profile around the particle will change, because the boundary condition for the temperature or the concentration is being applied at a different location as the diameter decreases. Okay. And in those cases also, the temperature or the concentration of the surface will evolve because the diameter is changing. Okay. So, we will examine in that case as well, the steady state approximation can be used if the time scale for the decrease in the diameter, for example, is much smaller than the time scale for the diffusion around the object, or the time scale for the velocity field to develop around the object. Okay. So, in that case you can use the diffusion, the steady state correlation for the dimensionless flux, okay, the Nusselt number or the Sherwood number. We will examine the dissolution of a camphor particle, okay, in the next lecture. Okay. The camphor particle dissolves because the concentration at the surface, okay, if you had a particle of diameter d, the concentration at the surface Cs of camphor in equilibrium at that temperature and pressure is higher than the concentration far away, which we will assume the concentration far away is equal to 0. Okay. So, we are in an atmosphere where there is no camphor in the atmosphere far away from the particle, and there is camphor that is sublimating, that is from the surface of the particle, okay, due to the difference in this concentration. And we will do a similar balance equation in this case and obtain the time required for the dissolution of this camphor particle, and we will also examine the conditions under which we can make a steady state approximation for the dissolution of this particle. So, that we will do in the next lecture. I will see you then.